Okay. Hi everyone. I'll be presenting on the topic of post-OCR error detection and correction. So this project was led by Sharmila from November, December, and Sumit, Balaji, and upon our other collaborators. Since the presentations were getting a bit monotonous over the past 2-3 months because of the interns and stuff, I just tried something different. I didn't practice it so much, but anyway, hope you will like it. Yeah. OCR technology has been one of the success stories of the past 20 years for vision and deep learning. I mean, we can acquire vast amounts of information from historical documents. We can digitize them, search from them, retrieve information, and all other NLP tasks. We can extract a lot of knowledge from those documents. And the advantage is that it's faster, cheaper, and also secure as compared to, let's say, humans scanning and then annotating each and every letter. So, yeah, secure in the sense that there could be some documents that you don't want people to read. But however, over time, the technology has led to lots of errors. So OCR text has lots and lots of errors, and it leads to a very poor downstream performance in all kinds of tasks like co-reference NER, co-reference resolution, pause tagging, and so on, which I will show in some time. So why do these errors occur? Um, First off, because of the documents, right? So you can have like ink degradation in documents. So for example, choose the pointer. Yeah. So it could be because of ink degradation, where you just see some ink spots on documents because they get old, or because of poor scanning, or blurring, or old font, historical fonts. Bleed through effect, which is basically when the same page has both front and back printed. So what is on the back side will you can just see it on the front. So or it could be handwriting on pages. All these lead to like bad because OCR is heavily perceptual based. It messes up the character predictions. Uh, and all of these are because of historical documents and wooden printing back in 1600 1700. Even non-English languages, they also lead to lots of errors. You could have torn and burned pages, but it's not just historical documents. Even modern, like digitally generated documents like bills and contracts and invoices, it could be that they're torn, they're deformed. They could be scanned in a in they could be, the photo could have been clicked in a different viewpoint, or they could have been scanned in a different angle, or they could be shadows like this due to poor lighting and so on. So the impact of OCR errors, like you can see here, that as the so this is one experiment where they controlled for the character error rate, and as the character error rate increases to 6%, like the F1 score on NER like almost dropped by 25%, 25 points. The reason, as I said, is that it's heavily dependent on perceptual data, OCR engines, and they do not take like the word semantics or the context into account. Uh, but the nice thing is that these errors have some kind of structure. They are not just like random errors where you can every character just switches or something. But there is actually some kind of structure, like L gets seen as I, or J gets seen as L. Like for example, here in Juliet, you can see that just Li is recognized as II and so on. Uh, so it makes sense to build some mechanism so that these OCR errors get corrected and we don't face problems in NER. So one way obviously is to improve the OCR engine itself. Um, but the problem is that if you improve the OCR engine, you will also require the original images so that you can rerun the OCR engine on them. Original images are not always available. At the same time, it's kind of expensive in the sense it's people use all these big engines like AWS and GCP and Azure and so on, and it's difficult to iterate over them for a long time. Uh, a post processing step with a post OCR model makes sense so that you can iterate over it more frequently and actually fine tune to your data sets. So like we can see that the errors are kind of image specific also, right? So or data set specific. It could be that you have a certain historical document with certain language. So you can fine tune your post-processing test step to that language. Yeah, so who can save the day? Who can build this post-processing kind of thing? So here comes like the hero. So our hero BERT arrives with. So here in this presentation, I'll be using BERT or as a visual euphemism for Roberta or whatever autoregressive models which have this kind of structure. So the advantage of BERT for this particular post-processing task is that it has it has performed very well on all these NLP benchmarks, and it has lots of nice attributes. Like I'll say so he has lots of nice attributes, and like if you see all these Bertology and interpretability papers, they have found like really good meaning representation within the vector space of whatever these huge language models learn. And the advantage is that they can impart context and word meaning to this OCR text and can potentially help in corrections. So the problem formulation is as follows. So you have this clean text, somebody has written this clean text, and they then print or either via digital, they convert it to an image or scan and so on. Now this image is passed through OCR engine, and you finally get this OCR text, which we have seen it has lots of errors. You then pass it. The idea is to build this OCR model, which generates this post OCR text, which is as close as possible to the ground truth text. The problem is that OCR text and related images can be easily available, but this clean text is not something that we have available. It's also very tough to simulate errors, which I will show later. But roughly, this is the problem. You have this sentence S, which is the OCR text with S1 to Sn tokens, and you have W, which is the ground truth text. W1 to W1, they need not be equal because of white space errors and breaks and so on. So the idea is to get this W cap, which actually maximizes this probability distribution, and the loss is over W and W cap. But note that W is not actually available. It's rarely available. So our hero BERT, he starts off with let's say, he takes these pages and looks at this actually OCR text. This particular data set actually has the ground truth text, so he looks at both of them. But as you can see, there is a complete lack of alignment in the sense that so for example, this part together with there, which kind of lies here, and then it's easier to have, let's say, together with their last dying words in this ground truth text, but due to this formatting and due to the bleed through effect, the text gets the OCR text is completely wrong. And when you have two columns, this entire line is read as a single thing. That is how this text is, which is again another mistake, right? You can't basically align this OCR text and ground truth text easily so that you can map the tokens, the erroneous tokens to the correct tokens. I'll go through what errors are there. Mostly there are no errors in the document. Like most of the words have a none token, which is basically they have no errors. But there could be misrecognition errors where, like for example, this M gets corrected to R, and this is the OCR text. This is the OCR text, and this is the ground truth text, where this M is read as R space N, or there could be extra content where you can have a kind of a word break kind of thing, a space at random, which leads to some extra content. Or there could be content loss where content is like in the OCR, the word in ground truth is simply not present. Hyphenation, like typically in URLs or where there are line breaks, as in when you have to skip to the next line, you will have these line break errors. And the problem with all this is if you think of, like, let's just take some plain text and just add these errors at random and simulate lots of this, we can't do it because the errors are actually OCR engine dependent and also dataset dependent. The artifacts are dependent on these, and we can't just insert any edit distance one error. And also there is no link between the length of word and the error, because the white space could exist anywhere, and then you can't make such a connection also. And also computing these statistics is very difficult without alignment. So previous attempts at solving this problem of post OCR processing looks like this. So you have this OCR text, and then you have some error detection module, which generates all the errors, which identifies all the errors, and then for each error you generate a candidate, potential candidate, which could be something that corrects that error, and then you rank those candidates, and you take the best candidate and then you replace that error with the candidate. So for example, there was this white space error correction, which basically generated all potential, inserting white spaces in all places and seeing which one fits well using an n-gram model. But again, it has like this exponential complexity, which is very difficult to implement for longer texts. Our PDFs have like huge sentences, like so it's difficult to use this white space error correction module. Token similarity is something that is like when you see a word, and if that word does not exist in your dictionary, it is an erroneous word. So you replace it with the closest word in your dictionary. This works for errors such as this, where it notices R, and this probably wouldn't exist in the dictionary, so it is good for them. But when you correct, when the error is actually a good word, as in let's say A and AUNT gets printed as ANT. Now ANT is a word that can exist in dictionary too, so it doesn't work for them, this token dictionary correction. And spell checkers, like this is one of the oldest methods for spelling correction. You have these character confusion matrices. Like for example, this is a matrix for substitution errors. So M and N typically get substituted 180 times. Like that is one of the frequent errors. So you can use any of the older character confusion matrix and use it to correct its spelling mistakes. But as we have seen, the OCR errors are not necessarily spelling mistakes, but they have some other structure altogether. So within Adobe Dataset itself, the PDFs are very tough. They could be, like PPTs converted to PDFs, and it's very difficult to align them because of these spaces and so on. Like you have different paragraphs, and you don't have that alignment in the paragraphs itself. Like for example, so this is the OCR text, and this Louisiana, the word here starts here, but in the ground truth the word starts here only. So actually mapping the error token with the ground truth token is a very difficult task. Sometimes you also have things in footnotes and side notes, etc., which are again very difficult to align. Even tougher PDFs are these ones, PDFs with figures, where getting the alignment for text within the figures, the legend, and even PDFs with the tables, for example, they are like poorly formatted. Like this is one of the PDFs where the numbers are all jumbled, and there is text overlap and so on. So aligning this, you getting the ground truth text for this and aligning it with the OCR text, and then teaching your model to actually take this OCR text to ground truth, it's actually very tricky. So we try some shiny models, like edit language models, to solve this issue, where the input is like the ground truth text, the OCR text, and output is the ground truth text. But in this edit language models, we collapse all this print, this entire thing into an edit vector kind of thing. And all we do is the generative model is as follows. We sample a ground truth text. We then sample an edit vector and apply that edit vector onto the ground truth text to get the OCR text, and inference is the reverse direction. So yeah, I mean, that is the generative story. Uh, so this is like the overall generative distributions where we sample the word from the entire vocabulary, and VMF is basically it's like normal distribution only, except it's used for directional kind of thing. But the problem with, again, after learning this model, we noticed that we always predicted only uh, space tokens as the output. So you sample any edit vector and you apply it on any of this in the reverse direction on the OCR text, and you get the ground truth text, which is like only it has only spaces. So uh, and we tried other tricks also, like diagonal attention plus coverage, where you the idea is that since the dependence between OCR text and ground truth text is monotonous, so it makes sense for the diagonal elements to be in the attention matrix. The diagonal elements should be filled more prominently than other parts. So basically, word at the fourth position in output sequence is more likely to be dependent on third to fifth positions. This is especially true for this post-OCR, unlike, let's say, translation and so on. And copy mechanism, as we have seen that mostly there are only none tokens. So most of the words are error-free. So we just learn this probability distribution which predicts, let's say, to just copy the word from the input sequence. So we exhaust all tricks in the pocket, but yeah, I mean, we get very bad results. Uh, all tokens get either predicted to none, or very few misrecognition ones are corrected and so on. Like, forget about correction, even detection is not so good. Like, we are not able to detect any of these. Uh, so like most sentences are error free, and there are these few pages which have problems, but they are difficult to align. So it's like that. So the ones that we want to correct are in fact much difficult to align. So
इन जालिमों ने मिलकर तो तुम्हें सड़क पर लाकर खड़ा कर दिया। अब क्या करोगे शिवाजी? हे भगवती भवानी मैया, इनके धंधे को बरकत देना मां। मेरा हाथ बहुत लकी है, इसलिए बोनी मैं ही करता। भीख मांगो शिवाजी।
yeah, I mean, is this so we are basically like stumbled at this point, right? We are not able to correct anything, and we don't have any other way to go. Since we are not able to correct, or we are not able to align and so on, we retain only like the simpler paragraph things. And so we and within these JSON files, we also figured that we can get alignments between ground truth and OCR. So I'll show some examples later. And we can also get confidence scores within the word. So roughly, so this is what has spanned so far. So we can either choose to take this and correct only some of the errors, or we can, let's say, not stop doing this project altogether. But so that is the choice that we had at one point.
सिक्के के दम पर पट आया तो सीधा रास्ता, चित आया तो शेर का रास्ता। मेरा रास्ता ईश्वर तय करेगा या इत्तेफाक।
Yeah, of course, half the presentation is remaining and half the movie was remaining after this scene. So it is obvious what side of the coin it will be. So we do.
आज से मेरा रास्ता शेर का रास्ता।
So we this is basically our pipeline, like a standard post-processing pipeline. We take the OCR sentence and then we predict what are the error tokens. And given that, let's say there is this error in one of these words, we then correct that word character-wise to get the corrected token. This is roughly the pipeline. And after filtering, after removing, let's say, PDFs with figures and so on, like the errors have greatly like reduced. Like this is a bad thing actually, because we want to correct more errors, but because we can't correct certain PDFs, we filter them out. So like misrecognition errors have reduced from 2514 to 870. Extra content has reduced. All errors have reduced, but at least the good part is that these are much more aligned and much more like feasible to correct. These are the training data set details. Like you from 400 documents, we kind of end up getting like lots of none tokens and 9030 erroneous tokens. Accuracy. So the standard metrics are again accuracy and edit distance and precision recall. So accuracy is basically you average over entire data set. This is an indicator function. The output of the model should be equal to the like whatever is in the data, the label. But the recent NLP papers have come up with this, especially adversarial NLP papers have come up with what is called as robust accuracy. So robust accuracy works as follows. You again sample from the data set, test data set, and so you this is an attack surface. B of x is an attack surface. So you consider all perturbations of a token, let's say x or a sentence x bar, and your model should predict the right thing for each of the perturbations. If any one of the perturbations goes wrong, then the robust accuracy reduces. So that is the meaning of this equation. Like this is like very difficult to compute, right? Because the number of perturbations, let's say of a sentence, let's say the sentence is of length 10 and each word is of length 5. Then the attack surface is going to be as large as, let's say the attack surface is just those where words are within the edit distance 1. Then the attack surface size is going to be like within a word you pick one position and then you have 26. You can use any of the characters for that position, and you can do the same for each word in the sentence. So this is like huge complexity. You can't basically iterate over all the perturbations and compute this. The advantage of our scenario is that as we have shown earlier, there is certain structure in the OCR errors. So you actually have a shrinked surface. Like hopefully this is still large, but the hope, we haven't actually exactly computed this, but the hope is that we can compute this because of a shrinked surface and so on. This will still be the like this is the lowest bound of accuracy, right? You can't whatever other accuracy on shrinked attack surface you compute will be higher than this. Yeah, since we have reduced the errors that we are correcting, we get much better performance, in the sense we get an accuracy of 95% of the model. So the error like none, again lots of errors are still predicted as none, and there are some wrong correct tokens which are sadly predicted as error, but roughly we do like much better than, let's say, just predicting every token as none. So we also evaluate on ICDAR dataset. So ICDAR is one of the public datasets which has this kind of it has aligned OCR and ground truth text, and the advantage of ICDAR dataset is actually a good example of how to frame this OCR and ground truth data. So it has this perfect alignment between, like, for example, let's say this is the OCR text, then their dataset actually contains like where we need the alignment and what is the exact alignment with the ground truth with the spans. So preparing something like this on a large scale is very difficult, where you need a human to actually sit and like label each span exactly. So like, for example, there is a H missing here. So like if you think of our scenario where we have to, without this kind of spanned labeling, we would have mapped LONG to LONG HOW and this OW to, let's say, a noop token. So where like that is the difficulty of correcting these kind of strings. Unless you have the spans exactly, like the span in the OCR from L to W corresponds to the span in ground truth from L to W, then you can correct it, but otherwise just token level it's very difficult, which is what we were trying. So some takeaway. So that is the advantage of ICDAR dataset. The takeaway is that like the dataset is like really good, but it is again of a particular type of documents of it, and the labeling that we have in this, we can't get the same labeling, let's say in Adobe dataset. Some qualitative examples from Adobe dataset are like we are able to correct misrecognition errors, and we are able to detect and correct this. It is actually kind of difficult to detect this hyphenation thing, but misrecognition ones are like fairly easy to detect. Again, here is another correction. Sometimes numbers also go wrong, but we were able to correct them. Yeah, so actually like so for example, this particular error here, the hyphenation error, this is probably like a very small error as we can see, but the evaluation metrics of both like what Adobe uses and like the PMs use and so on, they don't capture this kind of thing where the importance of these things. So we will need to correct all of them to get a good score on the evaluation metric. But in reality, some errors are more glaring than, let's say, something like this.
क्यों हिला डाला ना?
गलत कर दिया तुमने शिवाजी, तुम्हें भुगतना पड़ेगा। बड़ा अपमान कर दिया तुमने मेरा। जवाब तो दूंगा। मैं बहुत सेंसिटिव हूँ, सहा नहीं जाता मुझसे। पलट कर वार तो करूंगा।
So indeed, the model is very sensitive, and as I said, the errors are very difficult to correct because it's difficult to map those tokens to their right token. So these are some more examples where spacing and spelling corrections are these things. Like for example, this L, this is a very common error where this it should actually be capital I, but it is recognized as small l, or let's say M is recognized as RN. So these things get corrected by our model. But error correction as such overall is like very low. Like we are able, even after shortlisting the dataset, we are actually able to correct only like 10% of the tokens, and we are not even sure like whether the alignment is good within this, whether this accuracy even makes sense. So but roughly all the like the misrecognition ones are the easier ones, as I've shown earlier, to correct. So we are able to correct them, and overall before correction we computed the edit distance. On average it was like this much, and after correction the edit distance has reduced. So this is something good, but the accuracy is like very miserable. So the reason, I'll go through the reasons why the error correction is difficult, and obviously it is because of. So one of the limitations is like the bad ground truth text, right? So if the ground truth text itself is wrong, like for example in Adobe's dataset, for some reason Y is missing in many of these words. The second limitation is bad alignment. Even within this gold JSON files that we have, the alignment is not good. Like so this actually the test basically means the OCR thing. The letters obtained were did exist in the OCR text, but they were shifted to the previous dictionary element. So basically the gold JSON itself had bad alignment, so we can't we can't map, like you can't train your model to correct ing to obtaing, or you can't, so that is like very difficult, and your model can't learn such level of dependencies, which is why our detection is good. Like we are able to recognize that, let's say ing is probably an erroneous word, but correcting ing to obtaing is like very difficult. Even with context, like the BERT model actually considers all this context, but since Adobe dataset itself is like a separate thing, which BERT is probably not trained on it. So I mean the vector space of BERT, pre-trained BERT.
तीन।
गिनता क्या है बे? हाँ?
तुझे वापस जो देना है।
अबे तुझे जिंदा छोड़ूंगा तब ना।
So the third one is boundary errors. Now, as I mentioned, these are like the most trickiest of the errors to actually solve, despite all these alignments. And this is where I'm actually talking about the alignments that Natwar mentioned. So, so for example, here in this OCR text, when you have L space I space T, where do you map this L2 in ground truth, or where do you map I2 in ground truth is not clear. If you map L to, let's say, the token literature, that is difficult to correct. So we introduced something like the noob characters, where uh, we add these noob characters to the ground truth itself, so that the character level BERT model learns that the space between L and I in OCR, this space should be mapped to a noob character, or no character in it should be corrected to a no character. And we we use all these schemes like this recursive text alignment scheme, which basically finds unique words between OCR and ground truth and uses them as anchor points uh, to figure out the alignment. And we also use like this in biology. This is a very common thing to do, called Needleman-Wunsch algorithm, where you have this you have two DNA sequences which you want to align. So this is a very this alignment algorithms are used very frequently in this. So we use that too. But again, the point is that errors. These are the places where errors occur, and sadly, these are the places where we use heuristics also. So because of which we are, as I said, the things that we shortlist and have very few relevant errors, and the things that we don't short, and even within that we have all these errors. So and wherever we use heuristics, like let's say these LCS or retas or using BioPython, we it's just another layer of complexity which leads to, again, poor evaluation scores and so on. Another interesting thing is that it could be that these two models they suffer from the same thing, right? Like maybe OCR and post OCR, both of them are suffering from the same problem. So maybe OCR also, the engine, Iris engine within inside it, it uses some kind of this alignment and so on, and it didn't work in OCR, so why should it work in post OCR? So it could be similar pathology. Um, regarding So, is there a way to improve, or there are some avenues to improve? Like, for example, maybe if we can actually manage to generate more and more data from clean text using a much better scheme, maybe understand these probabilities of how these errors occurs and structure, and simulate lots of these pairs of text, or maybe use the visuals itself, like the image itself. Like, since we have the image with us, it is not often, as I mentioned earlier, that images exist, but we can use the image itself as part of post processing step, and maybe that can also lead to improvements. But again, if you start to use images, and if you start to use everything that is taken at input, then why don't you just put this post OCR in OCR itself, like improve the OCR? So those are kind of questions that we don't know. But if Shivaji movie teaches us anything, it is that you can always make comeback. So yeah, as I said, we hope to use the visual text, and Genealog is a new library that helps. A very recent library released in June by Microsoft, which helps us simulate document images. So our idea is to pass these document images through OCR engine, and like everything will be in our control, alignment, everything will be in our control. So So this is one idea. And visual text embeddings, as I mentioned, maybe use the visual, the image itself as part of post-OCR pipeline. So these are some improvements that we hope to make it work. Yeah. Thank you.